So let me continue. What I'm trying to do is to get the students to take to mathematics like ducks to water. And this is a study on the lessons that I learned from a case study on investigating the correlation between self-assessed capability and the actual competency of the students. So the talk's going to start with an introduction. I'll talk about the problem that I faced, my proposal to solve it, and just show you some can-do statements. Introduce the case study. Now, strangely enough, I teach computational linguistics at a university in Japan, and yet this was teaching mathematics to school children in Thailand. And I'll talk more about that. I'll give you some very, very basic quantitative results based on a very small sample, which we can't generalize from. But I want to focus on the reflection on practice, what I learned as a teacher and the lessons that I've taken away. So this is more of a sort of a pedagogic presentation rather than telling you anything about statistics and mathematics. So the problems. Essentially, my problem was the students were spending a lot of time on testing. So at this particular school, they test, they have a midterm test, they have a post-test, and so much of the class time was dedicated to testing. I would imagine that I think 30% of all the teaching time was not teaching, it was testing. So kind of my problem is kind of like, when we're testing mathematics, what are we really testing? We're testing their performance on an individual day. That doesn't necessarily mean that's their competence. And competence doesn't mean that's their understanding of something. And just because they can attain something on one day, that doesn't mean that they're capable of attaining it on some other days. Maybe there was a fluke, there was something wrong with it. The key problem is the brain's a black box, and understanding itself is not measurable directly. We have to look for something that's measurable, an observed variable, and then we think of the latent variable, which is got to be inferred from some other variable. So we've got a proxy variable, and what are we really measuring? And that was my real issue for the so much testing. So my proposal, and many teachers may like this, reduce the time testing, which means the reducing the testing administration, reducing the grading, and spending more time helping the students learn. There are issues with this because of accountability and governments and in terms of tutorial schools, they want to prove to the parents that the students are learning. So I understand there are practical issues connected to this, but as a teacher, my aim is to kind of like increase teaching time. So this was what I tried to investigate using can-do statements. Here's a sample of a can-do statement, not the ones from my school because they were in a different language, but these are written in English. And essentially, students look at a statement and decide, do they agree with the statement or not? And there can be a scale of agreement. This particular one says, I don't know it yet. I need help from a teacher. I sometimes need help, or I can do it. The one at my school was a simple, yes, I can do it. No, I can't do it. Dichotomous choice. So how much, if the students say they can do it, can they really do it? How much should we believe? So this case study, as I said, was very small, okay? And because it was small, I couldn't make any generalizations, which is why it's a case study approach. The context, so I was delivering, during the summer, I was in Thailand, and rather than teaching face-to-face because of COVID, all tuition was online. I delivered the tuition in English because all the students were attending an international school, an English-speaking international school. I delivered one series of lessons on probability, just 4 lessons, very basic probability issues. There were 6 students, all from the same school. However, they weren't in the same friendship groups. They ranged from 14 to 16, and there were 3 friends and 3 people who didn't know each other until this course started. By chance, everybody was female. 2 were Thai, 2 were half Thai plus some other nationality, I'm not sure what, and 2 were international, and actually their mother and father were different nationalities. So kind of that was the makeup of the class. What did we study? Well, it was a mixed level class. My only remit was cover probability and review probability. So in this class, we had some slightly, not quite gifted, but some kind of like bright students. And we had some students who were struggling and had problems keeping up with their grade level. The classes were four classes. The first one focused on basic probability and introducing standard notation using dice. The second one was focusing on coin tosses and thinking about how assumptions impact things and contingent events. The third one was a little bit more active, trying to get them to move around and do things and work together. Rock, paper, scissors game was a great way to think about possible combinations, permutations, and introduce Venn diagrams. And in the fourth one, we used this sort of 4 selection game as a way to review things. I'll probably just describe it quickly here since I have time, so we can kind of think about it. So we get students to choose a country beginning with D. In fact, we can try it now. There are 5 countries beginning with D. So the student chose one. Now they choose an animal beginning with the second letter of the country they chose. And then they state the color of the animal. And almost every student says the color is gray. Well, why is that? Even though there are 5 countries, most people can only remember Denmark. And because you remember Denmark, you think of an animal beginning with E. An animal beginning with E, elephant is the first that comes to mind. Of course, there are many others, but they're just not easy to think of. And elephants are gray, hence we get gray. So kind of like it's kind of like a very interesting kind of like way to introduce the idea of all those probabilities, and yet we can still, for the majority of students, guess gray. So the data collection, three types triangulated. There was a pre-unit test and a post-unit test. This is imposed by the school, not by me. Okay. There are assignment scores. So each class, the students have to do some homework. If they're lucky, they can finish it during class time, but mostly not. They finish it after class. And I kept a reflective journal on thinking about the lesson itself, the micro decisions I made in the lesson, how I could teach things better, given the parameters and limitations of the tutorial school. Okay, so I think you have everything here. So the can-do statement had just 11 statements. Do they agree or disagree with them? Assignment scores, most of them are graded automatically using the learner management system. And it's a simple pass it or repeat it, kind of adopting a mastery learning approach, which is the selling point of this particular school. My reflection on journal, of course, is kind of reflecting on practice, first promulgated by Sean, but there are many other people who've used this afterwards. So the results, very basic results. So you can see the can-do statements here, 11 statements. There are only 6 students, and we can see like 5 or 6 students in general in the post-test agreed with the statement. And in the beginning, it was sort of between 3 and 5, in most cases, agreed with the statement. So there's a slight increase. There's no way I can claim any statistical significance for these, but in general, it moved in the direction where I expected it. Had it been the other way, there would have been problems, right? So what do I believe from this? I believe that the students appeared to know what they did not know. Why is that? Well, when I checked the students who repeated more assignments, and they actually repeated more assignments in the ones that they said they didn't agree that they could do it. So you can see there's statement 6, I can calculate combined probability of mutually exclusive events. Okay, this was a low score in the beginning of the course, and the students repeated multiple times there, so it kind of correlated quite well, although I didn't try to prove correlation. So the reflection on practice, what did I find in my journal, reflective journal? First, a key problem was blocking language, okay? Students had real difficulties coping with some sort of ambiguities in the words. And when I was making this presentation, I noticed the word lesson. So like we can use lesson as something that you've learned. We can use lesson to talk about one individual class. Okay, so there's this ambiguity in the word lesson. And mathematics is full of these ambiguities. One student at this level, okay, didn't know the word subtraction. Then you take away and then you minus, but they didn't know what subtraction meant because it was just a little bit formal and they weren't familiar with that. So we can see the language of instruction could block the understanding of the mathematics tasks, the rubrics themselves. Difficulty applying knowledge to the problem. There's one thing being able to mechanically do something. Many students learn how to differentiate and integrate, and they know the mechanics of it, but they don't really know what it means or how to apply it. And that was an issue. Kind of one of the students noted, I can do it when I know what numbers to use. Okay, outdated examples. I'd use dice for things and just assume that the students were familiar with dice. No. Nowadays, they play massive multiplayer online games, and board games using dice are just, it's old hat, and that took me for a surprise since I was brought up playing Monopoly. Bias in selection, even though there were just 6 students, I noticed that I tended to select the students who looked eager more than the students who looked away, and it seemed to be a little bit unfair. So I decided halfway through the course that I would use a randomizer and kind of just let the randomizer select which students had to do something or had to answer or try to answer the question or share their ideas. Lessons learned. So I'm going to present this in using ducks and horses connecting to water. We can take a horse to water, but we can't make it drink. Can we make them learn mathematics? So lessons learned. For me as a teacher, it's never receding horizon. Despite the multiple training courses that I've been on, despite trying to improve myself, I find that no matter how often I teach, there's something that needs to be improved. So we're never going to become a great teacher. We're always going to become a teacher that's okay, but you know there's somewhere better. There's always something that we can improve. Shifting sands. So this was connecting kind of like my school experience of being taught mathematics to the way that I was teaching mathematics. So I was taught in a lockstep approach where the teachers lectured me, and then I sat down and I did multiple exercises until I'd mastered the mechanics of it. However, nowadays, students are expected to chat together, solve problems together, and share their ideas. All of these are totally valid learning styles. And for people who are sort of more inclined to to enjoy the sort of social constructivist approach, it works well. But what about those students who are reticent communicators, who like to think deeply about problems, but just don't want to talk to other people? So maybe it's a disservice to them. Encouraging belly flops. So kind of like, if you're going to dive into the water, sometimes you get it wrong. And it's the same with mathematics. If we can give the students chance to struggle, and this was mentioned by the previous speaker, yeah, give the students chance to struggle with a task, they may rise to the challenge and succeed and break new ground and achieve one of those eureka moments. But if you just mollycoddle those students through, spoon feed them on PowerPoint little by little, it's great in the beginning, perhaps, but we've got to throw them real problems to kind of get their teeth into and challenge themselves in. And this was some issue I had with the tutorial school, which adopts this mastery learning approach. So I think kind of a 2-STEM approach, combining a systematic step-by-step approach along with these big challenges, forcing students to kind of struggle with ideas and seeing how they can apply the knowledge that they have to the situation. Follows the red flags. And here's my swimming analogy. You don't tend to throw children into fast-flowing rivers to teach them how to swim. You might throw them into a small pond, okay, although I don't think I would do that with my children. I would teach them to swim first of all, and then show them the dangers of rivers and riptides and dangerous dams. But you don't do that until they can already swim. But once they can swim, we've got to show them these meaty challenges. So kind of, if we throw them in too deep, they may just flounder, which comes into this one, in the deep end. What's the balance? When do you decide to throw students this meaty challenge? And when do you let them just struggle with the small little wins? Okay, and I'm not sure. I think probably, as I mentioned, kind of like a dual approach. You throw out a meaty challenge, and then you let them have these step-by-step incremental challenges at the same time. And that way, the student who wants to rise to the challenge can sink their teeth into it. And the student who's more comfortable getting grasp of the field little by little is also kind of quite comfortable learning that. But I think it's a disservice to only provide one of those. I think the students need both. So that was what I learned from my experience teaching the children. Normally, I teach graduate students, so it was a novel experience for me to kind of enjoy spending time with younger children. Okay, so that's all I have. If anybody has a question, it'll be the first, but I would love to answer it.